my screen, and this is me. So I'm a assistant professor at Carnegie Mellon University, and I run a research lab called Morphing Matter Lab, and we basically study the tools, the mechanism, the computational design algorithms, and also the application of morphing matter. And morphing matter is another way to say shape-changing and property-tunable materials. And we make all kinds of materials transform. For example, we can make bacteria morph in response to moisture. And if you place those bacteria on a piece of fabric, then you can make a sweat-responsive fabric. And in this case, when the dancer gets sweatier and their body gets hot, the fabric will open up and help the dancers to get rid of the body heat. And you can also make food dance. I'll talk about a project related to shape-changing food. In a sense, make your molecular cuisine morph. And we can also make a physical artifacts morph. So for example, we can make a shape-changing lamp turning to this organic shape from a single line. And I also prepared a very short video clip, just let my students explain to you what does it mean by morphing matter. And they call themselves morphers.
Oh, Li-Ning, now we don't see the video unless nothing has changed yet.
Okay, I realize that's the case. I apologize. Let's retry. After using Zooms 1,000 times, there are still mistakes. But Richard, what's the preference? Should I go from the beginning or I should continue?
Start over.
Start over. Okay. I think it makes sense. All right, start over. I think you guys should see my slides progressing now, right? That should be right. Okay, this is the page when I said I ran a research group called Morphing Matter Lab, and it is to study the tools, the computational algorithms, and the mechanism of shape-changing material. And we call ourselves morphers. So we basically make our daily artifacts and material transform. And this could range from a bacteria that responds to sweat to cheaper and more easily accessible material like fabric or paper. So this is the sweat responsive garment we made with the bacteria from the previous slides. So basically, if you coat those bacteria on a piece of fabric, the fabric becomes responsive to your sweat. And this will help dancers and runners to get rid of sweat when their body are getting hot. We can also make food dance. I will show you guys a project that related to shape-changing food. And this is another project. We basically make a shape-changing lampshade. This will transform from a single line to an organic form. And then I also prepared a short video to let my morpher students to explain what does morphing matter mean to them. This time the video will play.
I am a computational designer. To me, morphing material is artificial nature.
The pandemic has disrupted some of my specific research. So, for example, I did not have access to the textiles lab knitting machine that I use for a lot of my knitting-related research.
I am a material scientist. To me, morphing matter is nurtured.
I am an industrial designer. To me, morphing matter is all about harnessing natural phenomenon and getting inspired from nature.
I am a computational designer. To me, morphing matter is aquatic.
I am an IT engineer at CMU. I love to combine technology with textiles in order to move clothing from its aesthetic function to a tool that can be used to solve human needs with the aid of technology.
I'm an architect engineer and a computational designer. To me, morphing matter is enhansive.
I am a computer science student. To me, morphing matter is evolved.
I work at the intersection of classical handcrafts and robotics. To me, morphing matter is about redefining the way we relate to material and craft.
I am a mechanical and biomedical engineer. To me, morphing matter supports the human body.
I'm Fong. I am an electrical engineer. To me, morphing matter is self-healing.
As you can see, we are trying to push the application domain of shape-changing materials from all the way accessible body support to fashion products. And when I show all these projects to design students, they often ask, well, I don't have any material science background, maybe I can code, but what is the trick? So I think about it, and really it comes into a very simple answer. You should try to make friends with materials. I bring a few of our design practices to explain what do we mean by making friends with material. So lesson 1, making a friend with material means you acknowledge and fall in love with her imperfection. So I introduce an imperfect material that is thermoplastic. So maybe if you have experience printing thermoplastic with low-end desktop 3D printer like a MakerBot or Ultimaker, you know what I'm talking about. This is a special effect called warpage. Basically, the whole 3D printed piece got off your print bed in the middle of a print, and you basically failed. So this is an imperfection that's inherent to the thermoplastic material. And to explain it a little bit more, so for example, PLA or ABS plastic are made of polymer chains that like to stay in this random chaotic states, that's its lowest energy states from a chemical structure perspective. However, when you print those filaments on a printing bed, you are forcing the polymer chain to go very straight. But the polymer chain does not like to stay straight. As a result, it tends to shrink back to its chaotic mode. And sometimes as it shrinks, it'll pop off from the print bed. That causes a failure. You know, engineers are trying to fight against this phenomenon to get better printing quality or get better injection molding quality when you do a plastic injection molding parts. And we were thinking about how to acknowledge this imperfection of thermoplastic. So if you print this tends to go straight plastic on top of an inert substrate, what you can get is a bending behavior. So we are making a bilayer material that will bend. And then with your engineering mindset, you can precisely control the bending angle of this bilayer structure. And with that, you can start to design interesting shapes. For example, you can make a flat disc with specific bending design. You can transform it into a piece of rose flower. This is the process. Again, we are using a super cheap desktop printer to print the flat sheets. And then you can dip it in hot water, and the water will trigger the bending motion and morph this flat piece into a flower. And worth to mention, so if you print this rose flower with conventional 3D printing approach, right, it takes 8 hours and a lot of post-processing work to get rid of all the supporting material. With our method, you only take an hour to print, and there's no supporting materials you need to process. And you can now unleash your creative power as a designer and think about all these interesting shapes you can morph from 2D to 3D. And this is one of my favorite, thinking about the vision of a future IKEA chair that can self-assemble. You know, IKEA make flat furniture to save packing space, and they save them a lot of money. And our shipping method efforts, however, it's really hard to assemble some complex furniture from IKEA. What if in the future, right, you can have a furniture that self-assemble, you can dip it into hot water, or you can just apply heat with your hair dryer. You can also program this type of shrinkage effect into 1D shape. So here we talk about even within a single line, you can embed different contraction and bending behavior with very cheap thermoplastic in this case. And with the tool, you can design the bending angle and simulate the bending angle and generate the print file. So here it shows a line structure we printed that will morph into this wire-shaped rows as we designed in software. And go back to my IKEA story. So now you can have a flatly packed furniture, and we only embedded a bending behavior at the joints. So here I'm basically using a hair dryer to trigger the joints to self-lock. So now you don't need any bolts and nuts, no metal parts, and this whole chair is made of a single biodegradable thermoplastic, and you can easily recycle it. And that is some of the powers of how you can leveraging 4D printing and self-morphing material for future furniture design. So I have another lesson. Making a friend with material also means you discover the extraordinary from her ordinary. And I want to introduce another ordinary material to you guys, that is food, particularly that is about pasta. So we all know as we are cooking, you know, pasta or Asian noodle, the material gets very soft and it gets swollen. And actually, indeed, if you overcook, right, they get extra soft and you don't want to eat them anymore. And that is a very ordinary phenomenon. Not only you and me meet every day, but our grandmas and the grandchildren meet every day. So flours are majority made of starch, and starch is a granule that tends to swell in water. It absorbs water molecule and becomes softer and larger. And that is again, the ordinary property of your friend. But we can make it extraordinary by, in this case, introducing some surface grooves to the flour dough. So this is a simulation of what a piece of flour dough will do if you introduce surface grooves and cook them. So it turns out the surface grooves, those basically bumpy texture, can interfere with the swelling speed of the flour. And if you design those grooves nicely, you can control the morphing behavior of edible food. So here, a long, thin hair pasta before boiling is straight, and after boiling, it will turn into this very interesting helical shape. And this is a real-time cooking process of, like I said, a thin hair pasta turned into this very helical form factor. You can then program information into it. You can make your food becomes an emotional display. We made a fun application for one of my graduate students who would love to propose in an Italian restaurant. You cook a pasta, it turns into a heart. So we then went further to think about how we can programmably define the grooving pattern. So we basically used a robotic arm in this case and stamp the groove very precisely and perfectly. And with that, you can further engineer the precision of the precision of the morphing. So, you know, on the black table, these are all flat shape before cooking. And then on the plate, that's the corresponding shape after you cook them. And beyond it's just being fun and, you know, scientific, there are also practical reasons why we are interested in shape-changing food. One strong reason is we can save a lot of packaging space. Think about macaroni pasta, those cylindrical pasta. 67% of the packaging space is used to pack air. And if you make every pasta flat, we can save a lot of packaging space, and that contributes to the future sustainability of food. And we do think, you know, space saving becomes essential when we are experiencing space essential journeys, packing space essential journeys. So for example, for a hiking trip, you might get very picky about the packaging space you wanted to take. And we also think maybe, you know, those food ones can help the astronauts to eat authentic pasta when they are going on a Mars journey. Because think about space travel, space, packing space and transportation space becomes even more essential. This is just my postdoc who brought those flat pack pasta, cooked them during one of her hiking trip. So another lesson, making a friend with material also means you truly understand her. This story starts with a material called gelatin. And I was thinking, you know, I'm lazy. I want to cook food, make both myself happy and also my grandma happy. My grandma like very soft and small food, so it's easier to bite, easier to digest, like the right-hand side. And me, myself, I like longer noodles with good texture, you know, fun to eat. But how can I cook both food with the same material within one pot, within one process? And then I consulted one of my science friend, and she told me I should look into Jello. So Jello is made of gelatin, and gelatin has different molecular chain length, and the longer chain gelatin will dissolve faster. So then I'm like, okay, what if you basically compose a piece of noodle that combine both the longer chain and shorter chain gelatin? So for the shorter chain part that bridge the longer chain, they will be more easily dissolvable. And then what happens is, yeah, we made this dish. This is the chicken clear soup, and we cook the gelatin noodles in it. If you cook it for a shorter time, it stays long. But if you cook it for a longer time, it'll self-chop itself in the middle, and turn into shorter noodles, and then turns into like this cylinder shape. If you think about from a programmable material perspective, this is a self-de-assembly process, which is indeed pretty interesting technically. Okay, the next lesson, make friends with material also is to set her a free path. What do I mean? So I want to introduce a material called silicone. For a while during my PhD, I got really interested in playing with those kind of soft, stretchable material because they are very organic, they're biomimetic. Think about all the sea creatures. At that point, soft robotics became a really popular field. You know, there are scientists at Harvard, White Size group, they are making this soft robots made of silicone. If you pump in air, they started to transform in this very biomimetic way. So I was like, oh, as a designer, how can I, be more creative and even contributing to some technical aspects of this kind of research? And my intuition is to combine some hard material with the soft material. Maybe there's something fun. So I'm very familiar with origami, paper folding. So I thought maybe it's fun to embed a slightly more rigid folded paper in between this very soft, stretchable silicone material. This is what ended up to be. So basically, depending on the paper folds, you can get different transformation behavior out of the same stripe. So this is just a very simple stripe, but I have an embedded paper that has very specific folding pattern. You can see a stripe can turn into a helix, a bending, a disc can turn into this very interesting 3D shape. That's all because you're playing with the paper layer. And then we thought, what can we do with it? Oh yeah, you can make a stripe. If you pull on it, turn into a light bulb, and maybe it can light up. So the lesson here is, we didn't really start this project thinking of making a light bulb. That's biomimicry. It was really starting with this inspiration of combining soft and hard material, but then just set a free path and let the material develop the right application for itself. If that makes any sense to you guys. And then my last lesson, making a friend with material also is to spend time with her. So including myself, all the morphers in the lab, we really spend a lot of time in lab and try to make our hands dirty. Even the computer science students came into my lab. I tried every possible means to convince them, him or her, to get their hands dirty. And we also ended up spending a great deal of time just to play with the material. That also depends on whether the morphing we're looking into is a fast reaction morphing or a slow reaction. For example, the video that's currently playing is to do with the self-dispersing seed. So we've been looking into this rain-activated seed dispersion mechanism for a while. Rain-activated sounds very slow. Sometimes you also have to wait for the rain to come in order to observe the phenomenon. And those germination tests takes forever, easily a couple of weeks. So you got to be super patient when you are working with those kind of slow reactive material. And at that point, we try to get encouraged by scientists and artists who have been benefited from their slow observations. So for example, we realized indeed in the plant study world, scientists like Charles Darwin, artists like Paul Klee, and physicists like Iran Sharon. So when they are studying a very specific phenomenon, mostly to do with transformation, honestly, either as a growth process or as just an evolutionary process, we always spend a lot of time with them. And I do think patience is a really secret ingredient when you work with shape-changing materials. All right, as a reflection, so if we think about the design process, there are many ways to interpret the design process, right? So if I wanted to use these two analogies, so one possibility is to solve a problem, and the other way is to think about making a friend. So when we think about design as an approach to solve a problem, it's very goal-oriented. We figure out the goal, we find the right technical approach, we go for it. It's very straightforward, but maybe less fun. And the other approach is to make a friend. That's very curiosity-driven. You might be distracted along the way. You might end up just, going on a hiking trip with your friend, and you might end up getting really distracted and, approaching a goal that's not what you intended to achieve at the beginning. However, there are beautiful sceneries and there might be really surprising outcome. I really do think working with morphing material is more like making a friend rather than solving a problem. To summarize, in the journey of morphing matter, you want to make friends with material. With that, I'd like to thank all my curious minds and great colleagues who worked with me in the past, all the funding agencies. And yeah, if you guys want to know more about morphing materials, feel free to Google us. Thank you.
Thank you. All right. That was super fast, super interesting. Everybody who's here, feel free to ask questions. You can raise your hand or just unmute yourself and ask a question, or just ask questions via the chat. So I do have a few questions myself, but maybe Bola, you want to ask?
Yeah, hi. Hi, Lenin. I'm Bola. I'm a big fan of your work. Thank you so much for this amazing presentation. It's a little bit weird because I'm like looking at you on the screen. So I have a question about just I guess like the entire design process that you just described about making friends with materials. I completely agree with that message, and I guess I'm curious to know, as a designer, how do you handle uncertainty when just kind of playing around and not being goal driven? How do you kind of stay motivated, stay on schedule while handling like this high level of uncertainty in your work?
Yeah, it's a very good question, but also a very abstract question. So I don't have a uniform answer, but I actually do think timelines is good. I like to set timelines for myself and my students. I think it helps you to push progress. And there are a lot of uncertainties and a lot of frustrations. And sometimes you just have to embrace it. That's actually what I mean. Again, think about making a friend's analogy, right? You fall in love with her imperfections, or you embrace all the aspects of your friends. So give you example, like the bacteria garment work. We got fascinated to work with this shape-changing bacteria because it's a living material, and we can play with synthetic biology and grow material rather than engineer it. All these very good and high-level intentions pushed us to work with it. But once we got our hands on it, it was really frustrating. It's a very weak material. It barely moves. It barely actuates anything on top of it. And also the culturing process, we grow, so their quality control was really hard. From batch to batch, the performance were very different. And very time consuming as well. And then as they die, they lose their property. There's this time sensitive aspects as you work with them. And at that point, all the colleagues were like, this sucks. We can never imagine anything with this chip memory alloy. Those metallic actuators are much more stronger and powerful. However, I think we got a breakthrough when we accidentally placed this on our skin, and just see it started to transform by the little micro environment around our skin, because it's slightly more moist than the air. So then we decided the benefits of it is its sensitivity. And later on, we had other benefits figured out, such as, you can embed, because you can do synthetic biology on a living cell, you can really engineer it to glow in addition to transform. But anyway, so that project lasted for almost two and a half years. I wanted to say, when everybody lost the faith in the material you are focusing on, you should be the one who try to stick to it if you believe in it. But which material you should choose from the beginning, I think partially intuition, partially inspirations you absorbed from your instructors, right? From papers, from cutting edge research reported by New York Times. All these are possible inspirations. And philosophically, I don't think there's cheap materials or expensive one. We work with bacteria all the way to paper and plastic. So each one of them is very unique in its property you can unleash.
Thank you so much.
Yeah, hope it helps. But really, I think, we all know, I assume a lot of you guys have design background. We all know design needs perfection and dedication. And sometimes the truly amazing design comes from the details. And all these are really great spirits when you work with materials too. So all those subtle behaviors, they were not known, they were observed. And that's actually quite true when scientists try to study their subjects as well.
Mm-hmm, mm-hmm. I have another follow-up question. Just because you mentioned when you're when everybody's about to give up on your material, you have to be the one kind of saying, oh no, let's continue working on this. How important would you say collaboration is? I mean, I think we all know collaboration is very important, but in terms of facilitating that playful initial interaction with materials and observing the details that you mentioned, I kind of feel like collaboration helps a lot, because you as a person can only see so much, can only absorb so much, but when you have another person's perspective on what you're doing, it really helps. And especially if it's a much more sort of interactive, engaged, involved interaction, as opposed to just a critique that you get from another person.
Yeah.
Do you have any comments on that?
I think it also depends on personality. Honestly, I'm a person who loves to collaborate, and I basically, my brain works more actively when I have a channel to output. But there are also, I met really great students. They have to focus and they have to make kind of independent decisions. However, I think from a designer's perspective, I can say something. So I think there are superficial level of collaboration with scientists or engineers who have complementary skill set versus very in-depth collaboration. So again, the example, if you remember my gelatin noodle, I spoke really fast, but really the idea is leveraging the scientific principle that different molecular weight gelatin will have different dissolving rate to design a noodle that have programmable behavior as you cook them. So when I started to work with gelatin, I wasn't the person who know what's gelatin even. I of course don't know there's a concept called molecular weight that's associated with the length of the polymer chain, that's associated with the dissolving rate. But it was when I worked side by side with a scientist, she mentioned this. She mentioned it as a frustration because he purchased 2 batches of gelatin and suddenly realized the dissolving time was different. She was like, this is so frustrating. Let me purchase the original one. She was telling me, so we can have consistent experimental performance. But then I was like, wait, you mentioned different gelatin can have different dissolving rate. Oh, what about my like self-chopping noodle idea? So I don't believe she could be the one who came out with that noodle idea. I also don't believe I could be the one who know how to do it if I didn't hear her talking about molecular weight and dissolving rate relationship. So that's what I so-called deeper relationship, especially relevant to us, right? As designers, you just can't be afraid of, knowing more about science. So you are not looking for raw technology and think that you will be the bridge and express the functionality out of the technology an engineer or scientist hand to you. You have to be actively involved in this whole inventive process of technology itself, because the deeper you understand the scientific subject, the more creative you can be from the bottom up. Yeah, if that makes sense. But then designers are I think the design mindset is very, very precious. And you just, if you get more familiarized with, scientific subject, you might realize you unleash your new talent of being a technology creator as well. But only if you're interested in that aspect. Being a designer without knowing chemistry, I think you can also be great. Again, it's a choice. I would averagely think, if you are interested in physical design, that involves materials and processes, knowing more physical sciences will be helpful.
Thank you. That was a really great response.
Yeah. Yeah, it's just some of my own experience, honestly.
Thank you. Are there more questions from other people? Can be about really different topics. I have one question, which is you are developing awesome projects in a way, like creating science fiction projects. You're inventing stuff that didn't exist before. And for example, your example of the IKEA chair is such a good example. I kind of want that to now exist in the future when the next IKEA shipment comes here and it just self-assembles. But do you use sci-fi in your design process with the research group in the sense of, okay, we have now created this, and it already, of course, was super hard to even get there, to have this object to morph or change in a certain way. But do you then jump ahead 5 years, 10 years, 15 years, 20 years and imagine what could be? And do you visualize that and also kind of use that as a part of the design process, and also maybe to evaluate, or you can critically analyze what type of technologies there could be or should be in the world?
Yeah, good question, Richard. I'd say we have really good friends who are pretty much experts in fictional design, speculative design, and we kept communication with them. But in my lab, we didn't really have a very rigorous process to evaluate, the probable and possible future. I do occasionally host those independent study groups with more design students, and together we will envision things that slightly more fictional. For example, recently I started an independent group that's we call it many versions. We're still refining it. Biohybrid future, biohybrid ecology, bionic plants. But really the idea is in the future, you can imagine all these biodegradable but responsive and morphing artifacts. It's hard to say if they're animals or plants or robots, but they do something to the environment. Either is to helping other plants grow, monitoring fire, reforestation after a fire. So it's all about a purposely engineered biodegradable organism that can help future. And I try to encourage my students to not be constrained by what's possible with technology, partially because yes, we want to be imaginative. Partially, I do think each one of us, including me, myself, and my engineering friends, we all have their very limited technical knowledge. So we'd better set the vision first and then think about how to engineer it. But I would say you guys perhaps have much more rigorous process to go with imagining the future. For us, it's more spontaneous. We do background study, we think about ideas, we cluster them, and sometimes I will set high-level goals, either it's societal purpose or utilitarian driven. For example, this bionic plants research is more about addressing climate change, but that's a very big umbrella.
Very cool. Maybe future collaborations. I think Jill has a question.
Hi, Liang. Thanks for this amazing, inspiring talk. I just had a question regarding can you tell us a bit more about how you explore sustainable materials? And by sustainable, I mean naturally found or those which are ecologically sound materials. And how do you explore them for morphing? And what are the kind of materials that you've explored so far and experimented with?
Yeah, very good question, Jill. So I'm not sure if you guys noticed, today I played a little trick. So I always got invited to different talks and I'm like, I want to design a theme for each invited talk. So this is the first of the theory that's related to making friends with material. I will have a follow-up talk in a more kind of, actually a biomaterial conference that's related to literally bio-derived and biohybrid material for morphing. I'm not sure, although if you guys notice, a lot of the material system I discussed today are bio-derived, including the food that's made of gelatin and starch, and also even the thermoplastic I showed, they are biodegradable plastic. And also the seeds, the rain-activated seeds at the very end, that is wood material. So honestly, there's a very big spin of morphing material in my lab that's related to naturally responsive biodegradable material. Maybe you guys also noticed I didn't talk a lot about electronics. Although Richard and I came from MIT Media Lab, there are blooms of electronic side of experiment sensors, actuators, IoT devices. Sometimes we use it for specific purpose, but a lot of times the actuation behavior from our material came from the natural energy stimuli, like the rain, the sweat, the heat, the ambient heat, the hot water, boiled water as you're cooking in your kitchen. And it does actually again, from a design perspective, I think it inspired people to think about novel applications. So we can think about shape-changing food because it's inherently biodegradable and compatible material. If you are embedding electronics, that would be trickier. We are thinking about, helping with environmental conservations and reforestations. In that context, we are also thinking of material we don't need to recycle once it fulfills its mission. Another aspect is a lot of our morphing mechanisms are highly, highly inspired by how nature engineer its own morphing material. So actually, I have all those things in my background shelf. So this pine cone, I was making a joke today on Twitter. It was already getting into a very popular science kit for kids. So it's a naturally engineered hygromorphic materials, means it responds to water. So if you put this in a hot water bath, after a couple of hours, all the scales will close down. And if you put it back in open air, the scales will open up again. So this is a very intricately engineered nature smart material. And there are many, many of these kind of examples we study in the lab.
Thank you.
Yeah.
Thank you. I have a question from Clarence. How do you come around with the original concept? Does the research of the material come first, or does the idea prompt the research?
Oh, I think if I capture the question clearly, so it's material comes first or research comes first?
Well, I guess more concept first or material research first, I think.
Conflict.
Do you first have the concept and the idea, or do you play with the materials and make friends with the materials and then the ideas bubble up at that moment?
Gotcha. It depends. The truth, honest answer is depends. But I'm a strong believer that sometimes, because there are already so many voices, maybe not so much in Parsons, because you guys are so poetic and provocative when you think about design. But in general, in like a lot of other design institutes, right, in engineering schools, there's very big voice that's about user-centered design, problem-driven design, and especially, I guess, as of today, because we have so many social, environmental problems, there's a strong push for designers to try to address societal impactful issues. So I certainly think it's very, very important to keep all these, visions in mind. Whatever we do, we want to create a very positive impact in the world. But this does not only need to be utilitarian, it could also be experience. I believe, for example, creating beautiful poems and movies is another way to bring beauty and impact to people's life. However, I do think in our lab, we had also an equally strong emphasis on curiosity-driven and material-driven design process. That does mean that sometimes we don't start with solving a specific problem in the design process. We started by being curious with a very specific material phenomenon. But for a lot of examples I showed, again, because you're a talented designer, because you're working with a talented group of people, you started with the material property and processes, and then you often end with a very tailored and sense-making application that indeed contribute to some societal needs. Like the food project, right? Like the classic warpage story I shared with you guys. We basically started with those kind of interesting phenomenons. We hack around it, we experiment with different things, then we bring more rigorous engineering mindset to quantify the property, the phenomenon. Then we bring more computer science knowledge to compute it, and with the purpose of controlling it to a higher fidelity and higher resolution. And eventually we think about what's the best use of it. There are failed experiences. We started with something really fun, but couldn't know how to use it. But most of the time we ended up having really a fruitful outcome that indeed matter to somebody. I'm not sure if that's a, yeah, I saw one clause, maybe that's okay.
Everyone, we still have a few more minutes, so feel free to ask questions. I wanted to ask another thing, and that's a bit more about biography, I guess. You are from China and now working at CMU with your own research group. I was curious, kind of, what was your journey coming here? And then also right now, maybe are you in touch with universities in China? And how is the research landscape? Is there an interesting relationship and connections that you're interested in? And I don't know, we have the manufacturing mecca in Shenzhen, and we have engineering universities like CMU in the US. So where do you see yourself there?
Yeah, thanks, Richard, for asking that. It was a very interesting journey, and Richard also told me there are actually a few students zooming in from China. Yay, hey, welcome. We're still creating in pandemic. So I was born in Inner Mongolia. It was a very small village. I did my undergrad in China before I came to MIT Media Lab for graduate school. So I intersected with Richard back in Media Lab. I did think a lot of the experiences in my childhood influenced a lot of how I think about design today. Again, my pine cone. If you guys, curious to visit some of my older talks, I always start with the story of me picking up pine cones in the forest in Inner Mongolia. And that was my first natural morphing material lessons. And I didn't really have a lot of technology around me, not even computer. I think the big contrast also inspired me to think about how to bring digital information back to an analog world and think about a seamless bridging between the two worlds. Basically, that means I kind of hate computer and working in front of screen all the time. That's why, as much as possible, I get my hands dirty, but hopefully get my hand dirty in a high-tech way. And right now, as Richard mentioned, I graduated in 2017. I'm having my own research lab, although I did keep a very close communication with my older lab mentors. Richard knows Professor Hiroshi Ishii. And we sometimes still talk and co-author papers. I do think, although in the new lab, we had because I got freedom to define the vision of the lab, we had a stronger focus in material-driven design approach. In Media Lab, my older lab, directed by Professor Hiroshi Ishii, is called Tangible Media Group. It's really about the belief that we can embody digital information in physical forms. But those physical forms could be mechanical structures and electrically driven actuator structures. It doesn't need to be material driven. And I think this morphing matter vision was my new hobby, new love. And we also, I guess I'm trying to push more scientific contributions with those kind of design-inspired research as well. That was new to me after I became a professor, because with some of my experience in the past, I started to strongly believe design mindset is so precious. Sometimes you can inspire scientific research. So right now the lab, I think, is more interdisciplinary than the interdisciplinary lab I had at MIT. I'm also a adjunct professor in material science and mechanical engineering at CMU, supervise Mackie PhDs, for example. So I also, by the way, do occasionally receive inquiries from Parsons. So there are alumni wanting to do internships or jobs. You guys are super welcome to reach out. Richard, I don't know what was your intention. I could go on for 24 hours about my story, but yeah, I'm not sure.
I'm sure we would want to hear it. It's good.
Oh, one thing I want to add. I got the chance to visit Shenzhen a few times. So there was it's called Manufacturing Scale program. at MIT Media Lab, they basically bridge the students with some of the manufacturing facility and resources in Shenzhen. So a lot of our projects require, some sort of mass produced parts could be made in Shenzhen. That was a very inspiring trip. It was a whole summer. I think there are many ways we could possibly work with China, not only on the manufacturing side, right? Also cultural connection. I got, for example, ceramic students working with me, thinking about morphing ceramics. So she worked in Japan for 3 years with a Japanese ceramic master. And right now we are thinking how to combine some of the Chinese traditional ceramic technique with 3D printing. So yeah, there are a lot of kind of technical level, craft level, cultural level creations we can do as well.
Very cool. I have the last question here. Do you think morphing materials can be applied to the medical field?
Yes.
Or, sorry, this is a, I guess, two-part question. Or any future projects that could be inspired by COVID?
So the first question, medical field, actually we do have a few active collaborations with biomedical researchers. Name 3. So one was with a German scientist. So she reached me out wanting to understand whether morphing can be leveraged for implant, for example, the stent or some of the prosthetic implants for a breast cancer patient. Those you can deliver them in a much smaller compact form factor, and then they can basically self-morph once it's in place, triggered by some stimuli like a pH or specific temperature. And you need a biocompatible plastic for that. There was another project regarding drug delivery. So again, so you eat some drug that's super small, and then it goes into your stomach, which has a different pH condition, and then the drug will transform into a helical form. And as it transports from stomach to your intestine, it's stuck at the intestine. Think about a capsule turns into a larger fat helix and stay in the intestine for a couple of days. And then the drug can slowly release over this period of time. That means you only need to eat one drug for a week. For people who, who like to forget eating drugs, that could be an interesting approach. And it's a very active research area in biomedical field as well. Smart material being used. Yeah, and there was a slightly sci-fi one that's related to biohybrid robots. How can you create those kind of, what you call it, those organisms that are made of living tissues and living muscle and neuron cells. And they can be used as study organism to test drugs. I don't know, well, first of all, I didn't really find a very unique angle how morphing matter can contribute to pandemic that's super, super timely. There are 2 things we are trying to push though. One is about earlier days, because we can make flatly packed facial mask, and then you can basically mold around your face, and that's like a perfect fit. And then you can also make it reversible, go flat, and then you can easily wash it and you can pack it again around your face. There was another thing with the bionic plants we are trying to create, like my mom always wanting to know how's my plants doing. Now she can't visit me from China. So we were thinking how to use this kind of morphing plants to connect remote relatives. It's a very subtle ambient communication channel, but it functions as a physical media to connect people who can't really spend New Year's together. Yeah, but like I said, I think most essential thing is vaccine. And so I don't really have a very brilliant idea how morphing matter can really contribute to vaccination of the nation right now.
All right. I think we are at 8 p.m. in New York, at least, in Pittsburgh too. So thanks so much, Lining. This was amazing, super inspiring, I'm sure, for all the students. If you're all around, a round of applause in emojis or audio for Lining. Thanks so much. for coming to visit us. And I'm already getting requests from people if they can somehow reach out to you. So we're gonna try to make that happen. So I hope we won't bug you too much. And maybe for everyone else, I think our next talk is Tuesday in a week, and it will be, let me quickly put up the thing once more. It will be Ash Backus-Clark, and will be the event hosted by Black Beyond. And that Ash is part of Hydro Lab and should be,
2 weeks.
In 2 weeks, exactly. Tuesday in 2 weeks, so 2/23. And we're very much looking forward to that. Thanks everyone for coming, and thanks again, Li Ning. This is amazing.
Thanks, Li Ning.
Thank you.
Thank you.
Thank you.